Hi, and welcome back. So today we're going to continue our discussion of differential equations. And in the last video we talked about separation of variables, which is one technique used to solve differential equations. In this video, we'll be taking a look at slope fields, which are quite different than separation of variables, but this provides a more visual understanding of differential equations, and we try to gain some sort of qualitative understanding of differential equations just by looking at these slope fields, which are visual representations. So with that in mind, let's jump into it. What are slope fields? Is a very good question. So the first thing to know is that we can't solve all differential equations with separation of variables. I know, I'm upset about it too, because if that was the case, I would be very happy. So since we can't always do that, we need some other techniques. So one technique is slope fields, and this is a way to graphically represent the solution. So slope fields contain small line segments, and each of these small line segments represents the tangent lines of solutions of the differential equation at different points. And using these small segments which represent slopes, we can sort of estimate what the solution will look like. So on the right here, whoops, that's a highlighter. On the right here, this is what a slope field looks like. At many different points, we have these tiny lines, and what that's saying is that if there's a solution that passes through that point, I guess that's not a good drawing, but if there's a solution that passes through that point, this is what the slope of the tangent line would look like at that point. So it's like kind of putting together a graphical solution for us, but not entirely. So this is indeed the slope field for dy dx equals x, and you can see that as I was drawing, the shape that the lines are sort of making kind of resembles a parabola, right? And which is good because the solution to this differential equation, we can use separation of variables, we'll get y equals 1/2 x squared plus c, which is indeed a parabola. You might be asking that, okay, I like seeing this curve here because especially this line, it's tangent to it, and that is the correct tangent line. But what about something like that? Our curve doesn't ever reach down there, so why do we have this? Well, simply, it's because we have many different solutions to our differential equation, right? There's an infinite amount of solutions to this differential equation because we have this plus c term here. So all of these extra lines, though they may not correspond to other solutions, they just correspond to one, we still have those lines to account for all solutions with all of the possible values of c. Hopefully that makes sense. So here's a couple more slope fields to look at. Actually, this is the same slope field, but it's kind of visually representing what I was just saying. And here we have the solution curves for this, y equals 1/2 x squared plus c, and I plugged in c equals 3 different values here, so we get 3 different curves. And we can see that, okay, these lines sort of match up with the curve, and that is sort of what the tangent line would look near that point. And we can see, like, down here, we actually intersect, or we touch a tangent line there perfectly, also here and here. So these are multiple different solution curves, all represented by the one singular slope field. We're going to draw our own slope field, which is a little bit annoying, and it'll take a little bit of time, but it's good practice. If you're curious about the AP exam, I won't recall them ever asking you to do this, but this exercise will help us be confident with analyzing slope fields and what exactly they mean. So sketch a slope field for y prime equals 2x plus y at the indicated points, and sketch a solution that passes through 1, 1. So what do we need to do? Let's take a look at this point here first, which is located at -2, 2. We want to draw a small line that represents this which has slope equivalent to the slope of the tangent line at that point. So that means we have to solve for dy dx at negative 2, 2. Moreover, we have to solve for dy dx at all of the points represented on this grid. So let's do at negative 2, 2 first. This y prime is dy dx, so we just have to plug into this right-hand side. So this would be equal to 2 times negative 2 plus 2, which is equal to negative 2. Okay, so with that in mind, let's come over to this point here. And we need to draw our slope field, so we need to draw a small line segment. But our line segment should be drawn such that its slope is negative 2, what we just solved for. So perhaps that looks something like this. Maybe it's not perfect, but it's good enough. So that handles one point. Let's do the point right below it. So that would be dy dx at negative 2, 1. And we'll do the same thing. Plug it in, negative 2 here, plus 1 this time. That's equal to negative 3. So we come over here, and now we need to draw a line that has slope negative 3. So maybe that's a little bit steeper than the previous line we drew, so something like that. Okay, let's do the next point, negative 2, 0. So dy dx at negative 2, 0, that goes to 2 times negative 2 plus 0, which is equal to negative 4. And I'll do the one right below that as well. So dy dx at negative 2, negative 1. That's 2 times negative 2 plus negative 1 equals negative 5. So this one, we want its slope to be slightly more steeper than the previous one. So that would look something like this, perhaps. And then this final one down here should have a little bit steeper slope than the previous. So something like that. So not the best drawings, but you're sort of starting to get the picture. So let's do a point like this, and then I'll sort of show the pattern, and then we won't do all of them. So this is negative 1, 2. So dy dx at negative 1, 2, that's equal to 2 times negative 1 plus 2, which is equal to 0. So, and then let's just start to hypothesize what these next points will be. So here, the only difference between this point and the previous point is the y-coordinate jumps down 1. So we expect the value of dy dx to be 1 less than the previous one. So this should be 1 less than this should be 1 less than that, and so on. So if this is 0, this will be negative 1, this will be negative 2, this will be negative 3. And we saw that pattern here. So let's draw a small line with slope 0. That would be a horizontal line. Then we do negative 1. That'll look something like this. Negative 2, a little bit steeper. Negative 3 looks something like that. And now let's just jump through these and try to get through it. So I'll write the formula up here just for reference, 2x plus y. So we're at the point 0, 2. So that would be equal to 2. This will be 1. This will be 0. And this will be negative 1. And then here we're at 1, 2, this point. So this should have slope 4. So that'll be pretty steep. This should be 1 less, so slope 3. It's a little less steep. This is slope 2. And then slope 1. And finally, we're here at 2, 2. So that would have slope 6, which is very steep. Then slope 5, which is a little less steep. Slope 4, which is a little less steep. And slope 3, which looks something like that. And that's our slope field. Right? Just a bunch of these tiny line segments. But we can start to gauge what a solution would look like. And we're told to sketch a solution curve that passes through 1, 1. So we want it to pass through here. So what does the solution look like? These lines are all pointing downwards and to the right, something like this, and then it gets like a little bit, it's steeper here, but here it kind of narrows out. and then it increases as we go this way. So the curve should look something like maybe something like this, right? And we know that there's a lot of solutions to this, and it's hard to draw in a completely accurate one, but this best fits what we're looking for, right? It kind of passes through this point. I just didn't want to draw completely over it, but we can see that the tangent lines kind of match for the most part the curve. So this is what we would expect our solution to look like, something along that form. And then we can start to hypothesize what the shape of this would look as an equation. So that's our big slope field example. Let's take a look at something that you would probably see in a multiple choice exam, where you have to match the slope field with the differential equation. So for this, we actually won't use too much math. We'll sort of use our intuitions. So we can kind of group some of these together. B and C are kind of similar to each other in that they're both sinusoidal in nature, right? If I try to draw the shape that C is portraying, it looks something like that, which looks like a sine graph. And for B, it's something like this, which is also a sine graph. Kind of. Or a cosine, just shifted, doesn't matter too much. So we expect B and C to match to one of these two. It's just a matter of choosing the correct one. So how do we go about doing that? Well, let's look carefully at our slope fields. For B, whenever we're on the y-axis, if we're at some point here, 0, 2, 0, 3, whatever, the slope is always 0. So dy dx at 0, y equals 0. So we can plug in this point into these two and see where we get 0. So if we put 0 for x into this equation, cosine of 0 is 1, and 1 times a half is a half, which is not equal to 0. But if we put x equals 0 into here, then we get sine of 0, which is equal to 0. So B matches to the sine of 2x. So let's make that connection here. And we expect C to match with this cosine because of the shape of it. So now we come down to A and D. So we can try to graph what these look like here. This looks like that. And then D looks something like this. So they're kind of similar to each other, but it's kind of hard to tell which is which. So if we look at slope field D, the slopes seem to approach infinity as x gets more negative, right? So the smaller that x is, the higher the slope is. So let's think about that. Let's consider at the point x equals negative 100. We would want dy dx to be large. So between these two, when you put in negative 100, this will be e to the 200 power, which is huge. This will be 1 over 100, negative 1 over 100, so negative 0.01, which is extremely tiny. So that means D matches with this, and A matches with this. And just to show why A matches with this, to show why A matches with this, when x is close to 0, in this case, our slopes are very large. And indeed, when we put in a value close to 0, 0.01, 0.001, we get a very high slope value. So that would be matching slope fields. So this is a very common thing that you'll see on exams, so it's good to be familiar with this. And that concludes our short lesson on slope fields. So again, another tool to add to your toolkit, and yeah, hopefully you learned something. So until next time, take care.